Wow. We go. Always fun. Really hard deadline. About the deadline. Okay, so any questions before we get started? So on the board, it shows that I have finished all the partial credit grading. So everything's going to update on Canvas. If there's something that is actually not correct, feel free to email me. Okay, so second thing I want to mention is that there's actually not many lecture left, including today's lecture, there's only 7 left. Okay, and then you're going to have your midterm 3 right after the exam period. Okay, and after that, you're going to do your final exams. So this here is actually a plan. Okay, so these are the dates. Then we're going to have the remaining lectures. And I highlight the things we're going to go through. So today we're going to finish majority of the chapter 17B. Okay, so on Thursday, we're entering chapter 18. And next week, next Tuesday, we'll finish majority of chapter 18. And next Thursday, we're going to start our review for your midterm 3. Okay, so before the Thanksgiving, we'll finish all the review for your midterm 3. Then once you come back, once you start to take your midterm 3, we're going to do the review for the final exam. So that's the plan. Okay. I know after midterm 2, we consume so much energy, and then people just start to fall behind. Okay. And I guess now's actually a good time to get back on track. Okay. So typically, what I observed in the past couple of years that our section people should do much better than other sections in midterm 2. Okay, it's the same this year. Okay, we're doing great. Actually, we did great for the midterm 2. Okay. But the thing that can worry is that once the student feel like, okay, I can do well enough for my midterm 2, then I can spend much less time to my midterm 3. Okay, so one thing I observed in the past couple of years that in the midterm 3, our section typically perform slightly worse than other sections. Okay, and it's not because that we cannot understand the material, we definitely can, right? Because we understand the most difficult part. Okay. So it's simply because like we just laid back too much. Okay, we just enjoy the Thanksgiving too much. Okay, so the reason I actually highlight these lectures is because I want you to see if I am in your position, that will be my schedule. Okay, I want to actually make sure that I can give myself enough time to prepare my midterm 3 and prepare my final. Okay, so you have been doing great for exactly 2/3 of the semester. Okay, I know you're tired, I know you're exhausted, I know there's just too many final exams coming up, right? So now it's actually a time that this is called the final test every semester you're going to have, right? So how can you actually use your time wisely, which is something that's very important no matter what you do in the future. Okay, so life is actually very interesting. Okay, the older you become, people expect more from you, right? So greater capability, greater responsibility. It's always true. So people expect you to do more things. Okay, but your time is always limited. That means you can only be more and more efficient. So you can actually do the things that you like and still at the same time enjoy it. Okay, so don't give up. Okay, you are doing great. Okay, now it's time to demonstrate like how smart, strong, and beautiful you are by managing your time well for the very last month of the semester. Okay. All right. So any other questions for this? Okay. Again, okay, my office hour is my door is always open. So during the office hour, feel free to use me. Okay, if you cannot go to the office hour, email me. Okay, I respond quickly. Okay. All right, so if there's actually no more questions, we're going to do the second part of chapter 7b. Okay. Talk about equations. Okay, I will highlight the one that you need to memorize it. Okay, many of them just okay. Conceptual wise, it's good to have to know how things actually are developed. Okay. So first thing first. So we're going to learn a few terms. Okay, so 1, 2, 3, 4, 5, 6 terms, right? Many of the terms we have learned in the past. Okay, so in chapter 16, which we talk about the thermodynamics. Okay, that is actually a chapter that we start to connect the free energy, delta G naught, full equilibrium constant. Okay, right? So just to refresh your memory. That's actually how we write in chapter 16. Is actually one of the equations that you need to actually memorize. Right? Delta G naught equal to negative RT L1K. And then we also tells you for every single reaction, you can always write out your free energy, change of free energy of the reaction. Okay, it's going to equal to delta G naught plus T Ln Q. Right, so this is actually another equation that you have to know. So in chapter 16, apparently you're trying to associate this equilibrium constant K and Q, which you learned in chapter 13. Okay, that's where we learned the equilibrium. Okay. So in chapter 16, we tie them together. Okay. And then in chapter 17, we start to talk about the chemical potential, right? And then we're just going to do the same thing. We actually tie the chemical potential in a cell to your equilibrium constant K and chemical quotient Q. Okay, so it's always the same concept, okay? So that's why, see, we actually put this. What we're going to do is actually how we can actually relate those photons with your E naught and E naught cell. Okay, and then from the past, apparently we see this. If you have an E naught, you will always go with your K, right? If it's actually no little circle on the top right corner, it always associate with your Q. Okay, the same concept will apply to here. Okay, so how are we going to connect this one? This is actually the connection equation, which you also need to memorize it. Okay, delta G not equals to net N F E not cell. Okay, that's actually the first equation we have here. Okay, so this equation says that if you know a chemical cell with its chemical cell potential E naught cell, then it can actually relate it to your its free energy and the standard condition through the specific equation. Okay. So a few things you need to pay attention to. First, there's actually a next sign in front of it. Okay, it's negative N times F. Okay, so the N is the number of electrons that got transferred between your LoRa and GROC. Okay, so last week we actually introduced, we spent a lot of time talking about when you see a chemical redox reaction, how to balance the redox reaction in aqueous solution, right? So step number one is that you balance your atoms, right? So you balance your oxygen, then you balance your hydrogen under even acidic or basic solution, right? And the second step is you balance the charges. Okay. And the third step is that you want to make sure that electron got transferred from your LoRa to GROC. They are the same before we can add it up and get the final balanced redox reaction, right? So, and then step number three, you can intentionally look at, okay, how many electrons got generated from your LoRa and how many electrons got received from your GROC. They need to be the same, right? So, let number of electrons got transferred between those two half reactions. It's the N we mean here. Okay, number of electrons got transferred between your LoRa to GROC. Okay, so that's the N. Again, it's just a constant, just like the R here. Okay, but here, the specific number was found by the scientist named Berkeley. Okay, so that's why we use R to represent that constant. Okay, and then that's actually how scientists realize how we can actually tie the delta G naught to the E naught cell. Okay, so this actually is the equation that we need to actually memorize. Okay, so once you know this, the next thing what we do is actually we start to put these two together. Okay, because we know how the delta G naught is related to the K, and we also know how the delta G naught is related to your E naught cell. Therefore, we can tie your K to your E naught cell. Okay, so once you do that, okay, this will be the mathematical form of the result. Okay, so and the way you get to this is actually very simple, right? So focus on this two. You just divide the negative NF to the right, then you get to this specific equation. But this is actually not the equation I want you to memorize. Instead, I want you to memorize this. Okay, because in CHEM1312, we always talk about aqueous solution. We always talk about quantified fluidity. Okay. Therefore, all those constants can be combined. And once you combine all those constants, you can end up with a number of 0.025693. Okay, so for your calculation, that is actually the equation that you need to memorize. Okay, of course you can still memorize the formula, totally fine. Okay, but for the calculation, the one on the right is actually the one you have to use most often. Okay, so this is actually how you get to this specific equation. Okay, and then after that, what you do is actually very similar because you know your E naught cell is this form. Okay, then your E cell, which is compare the specific status of your chemical equilibrium. Okay, then you can express as E naught cell minus. I want you to compare to this stuff on here. So this is actually what we learned previously. Right? We'll write out the delta G of a chemical reaction. You write delta G naught plus RT natural log Q, right? So the first step is actually delta G naught is negative RT and K, right? So it's like you can consider first step is actually the equilibrium term. The second term is your fiber state you are, right? So different between the two will give you the delta G. Okay, so right now you want to actually replace your delta G, okay, using RT over NF. Okay, so it's actually a conversion factors overlay, but meaning-wise it is still the same. Okay, that's why when you write out your E cell, the formula is actually very similar. Okay, you replace delta G naught with E naught cell. Okay, and then minus a constant. Okay, times L and Q. So here in the original equation, you have RT, L, and Q, right? You have RT, L, and Q. Here is just RT over NF, right? So you convert, it's kind of like a unit conversion. Okay. So once you do that, and then for the specific condition we're always going to encounter in logic Chem 2, they will lead to this equation. Your E cell is equal to your E naught cell minus 1 over N. Again, the N is actually the number of electrons that transferred from your low rod to G rod. Okay. Times the same constant, 0.025693 times your LMQ. Okay, so this is actually how you further connect the E naught cell and E cell with your delta G naught, K, and Q. Okay, so this is what it is. And then previously we spent a lot of time telling you how to predict whether a process is spontaneous, right? And then the things I tell you is that we start from this, right? If your delta S universe is positive, then things will be spontaneous. Okay. Your delta G, if it's negative, then it will be spontaneous. Okay. So things your delta G is related to your E cell from this. Right? So you know the N number of electron that transfer, that term will always be positive. Where the constant is always positive. Therefore, your G, but there's actually negative sign here. So this is always positive. Where the constant is always positive. right? Meaning that the whole term in the front will be negative, right? That means that your E cell will have the opposite sign of your G, delta G, right? So since delta G, if delta G is negative, you have spontaneous process. That means you can actually add one more here, right? So this is like 1, 2. The third one actually tells you if your E cell is positive, then you're going to have spontaneous process. Okay? So those are the things that we need to actually have before we go to all the examples we want to go today. Okay, any questions for this? Okay. If not, then let's do it. First question. So this question is super long, okay? But information, I mean, you need to really learn how to actually dig out the useful information from the questions, right? So it says, a voltaic cell consisted of Pb/Pb2 plus half cell and Sn/Sn2 plus half cell. What's the value of the equilibrium constant at 25 degrees C? Using the reduction potential value for Sn2 plus is negative 0.14, Pb2 plus negative 0.13. Okay, so let's pretty much the questions, right? What are the keywords here? Okay, equilibrium constant definitely is actually a keyword, right? What else? Reduction potential, yes. Okay. Another thing I want you to pay attention is this word. Voltaic cell. Okay, I'm going to see this word a lot. Okay. Sometimes you will say galvanic cell, sometimes you will say voltaic cell. Left equivalent. Okay. So those are the things. This is keyword because every time we will see this, it's telling you the E cell has to be a positive value, meaning that your E naught oxidation plus your E naught reduction has to be positive. Okay, so that's what the keyword means voltaic cell. You'll see why it's so important later on. Okay, equilibrium constant K, right? So now you see, after I write things out, you immediately see that I have two terms. One is called the E naught cell. One is called the K, right? How is these two related? There's actually only one equation. Okay, let's go back to here. Do you see this? Do you see that? Okay. So what's around the symbols that or variables that you need to use? You will see there's actually only one equation contains everybody, which is the one we just highlight here. Okay, so this is actually the equation we're going to use, right? If I can know my E naught cell, if I can know the number of electrons that got transferred from my LoRa to GRA, then I can put in this equation to calculate my K, which is actually I think what you're looking for, right? So this will be the equation we want to use. Okay, your E naught cell equals to 1 over N times 0.025693 times LNK. Okay. So with that in mind, let's come back and reread the question again. Okay, then do our QD pack, right? The Q is actually we want to calculate the equilibrium constant. K. Okay. Then we check what's the data that we have. So it says the reduction potential of SN2 plus, meaning what? Right? Can you actually translate that the reduction potential of SN2 plus into the equation I just wrote? I hope the answer will be yes, right? Because you need to really actually know this what it means, right? So is SN2 plus, that's actually your reactant. They got reduced, meaning they got electrons. Okay, and then with electron, they reduce into the SN4. Okay, so how do you know that it's actually the things into right? Here, it actually provide you these reactions, right? So those things actually we call it redox couple. You will tell you what is actually your reactants, what are the species that show up in your reaction. Okay, it doesn't tell you who is the reactant, who's product. It doesn't say that. Okay, it just tells you okay, what are the species that is actually happening in this redox reaction. Okay, and then in the discriminant case, the reduction potential of SN2 plus, right? It's reduction potential of SN2 plus, meaning that you should start with your SN2 plus and write the electrons. And then based on your redox couple, we know the product will be SN. Okay, and then the notation you write at the very end, the E naught, right? The E4 is the reduction potential, right? So you don't need to write E naught, the E reduction. Okay, let's write E naught equal to negative 0.14. Okay, that's how I get to that specific equation. Okay, so let's do another one. It says the redox potential for your PB 2 plus, right? Therefore, I write PB 2 plus 2 electrons is going to equal becoming PB, right? So it tells you that. Okay, and then the reduction potential is going to equal to negative 0.13 volt. Okay, so apparently these are the two half reactions of your voltaic cell. Okay, but how do I actually get the inner cell from these two half reactions? You should see that both of them they are reduction reactions, right? But to form a battery, you have one oxidation, one reduction. Okay, let me actually split one of the reactions to generate your inner oxidation. Before you get adding up to get your inner cell, right? So which one should you split? Sn, right? How do you know it's Sn? Because we have this keyword called what? Voltaic cell, right? That means actually once you get your inner oxidation, and you add that to your inner reduction, the value has to be positive. Okay, so that means actually you will only be able to split the first one. Okay, so I have your oxidation potential, and the oxidation potential will be positive 0.14, right? And actually add up these two equations. Okay, so with that in mind, then you know your LoRa now should be Sn becoming Sn2 plus 2 electron. And you're going to have your E naught oxidation potential equals to positive 0.14 volt. Okay, G rock will be Pb2 plus 2 electron. That give you Pb, and then you have a reduction potential equals to negative 0.13 volt. Therefore, overall, you know your reaction will be Sn plus Pb2 plus 2 electrons, 2 electrons cancel out, becoming Sn2 plus Pb. Then you have your E naught cell equals to your E naught oxidation plus your E naught reduction, which equals to 0.14 plus negative 0.13.
Therefore, you know your E naught cell is going to equals to 0.01. Okay?
What's your N? What's your N? What's the electron transfer from your LoRa to Jira? 2, right?
Therefore, you know your N is equal to 2. Okay? So with these things being said, then you know your E naught cell is 1 over n times 0.025693 times your natural log k, right? Then you can actually use these equations. E naught cell is 0.1, n is 2, 0.025693 times your lnk. Therefore, your lnk is going to equals to 2 times 0.1 divided by 0.025693. Therefore, we can actually compute your k is going to equals to 3.4 times 10 to the negative 1. Okay, so let's actually how you solve this question.
Okay, let's recap these things very quickly. So in the beginning, inside the question, it tells you you have a low-tech cell, right? Low-tech cell is always the keyword. Okay, because you see that you know your E naught cell has to be positive. Okay, and after that, let's start to describe what are the redox couplers you have. Okay, you have SN2 plus, SN/SN2 plus, and TB2 plus. Those are two redox couplers, right? And then give you the reduction potential of each redox couple. So based on the concept of vortex cell, you can decide which one you can flip. So you have a positive E naught cell. Okay. So once you know that, then you write out your LoRa around your G-Rod to figure out what is the actual electron got transferred from your LoRa to your G-Rod. So you know the number for your N. Okay. So once you get your E naught cell, once you get your N, then plug into the equation. E naught cell is equal to 1 over N times 0.02563 times your LNK. Okay. Then you can calculate your K accordingly. Okay, so let's actually the logic of solving this question. All right? Any questions? Yes. How do I know? How do I know SN is lower?
Right, so LoRa is actually the species that lost electron, right?
Instead of got oxidized. Okay, so
I assume that you don't have a problem like when to actually flip this guy. This is fine, right? Okay, so if we decide to flip that guy, then you know that is actually a equation you're going to have, right? So when you look at the species on the right hand side, you start from SN, you end out with SN2 plus. Right. So oxidation number going from 0 to 2 plus. So the SN is undergo oxidation, right? So remember the LoRa means you lost electron. You got oxidized yourself. Okay, so that I know the SN is actually the LoRa. Okay, G-Rock on the other side is actually the species that undergo a reduction reaction, right? So you start from Pb2 plus, gaining 2 electrons. Okay, itself is actually reduced. So we know the other one is their G-Rock. Okay, does that answer your question? The vortex cell and the harmonic cell. Okay, so those are the terms that we covered last week, right? So every time you see those keywords, what it means is it's a spontaneous reaction. Okay, since it's spontaneous reaction, that means your E naught cell need to be positive. Okay,
So since you know it actually positive, therefore you know you need to put in your SN equation. Okay, is that clear enough? Okay, cool.
So that's actually the first question we want to go through. Okay. The second question is, okay, it says a vortex cell consists of two redox couple. One is aluminum becoming aluminum 3 plus, the other is Fe2 plus becoming Fe3 plus. Calculate the E cell when the concentration of Fe2 plus is 1 and Fe3 plus 3 plus is 0.1. Aluminum 3 plus is 0.1. Use the reduction potential for aluminum 3 plus negative 1.66, Fe3 plus 0.77. Okay, so what are the keywords? Vortex cell. Okay, and then you see this? Okay, so when we are in chapter 16, okay, when we start to introduce that delta G equals to delta G naught plus RG ln Q. Okay, when we do the questions, so I say specifically that if a question tells you a bunch of conditions of your reacting products, what I really want to tell you is they want to calculate what? You can see this. They start to actually tells you very specific items, right? Fe2 plus, Fe3 plus, aluminum 3 plus, right? And it tells you what's the concentration of those things. It's asking you to calculate the Q. It's always the case. Okay, so if you see in your written three, okay, if you do a bunch of chemicals and there's the concentrations, they're asking you to calculate the Q. Okay, so up to this point, okay, there are a few things already pop out, right? Because carbonic vortex cell tells you your equation must contain your E cell, right? And then it gives you a bunch of information of the chemicals. Your equation must contain Q. Okay, and then go back and check out the two equations it give you. You see this? E cell equals to E naught cell minus 1 over n times 0.025693 times ln Q. Okay, that will be the equation that you are going to use. Okay, so that is actually the really quick way to actually identify what equation that you use. Okay. All right, so then we can go back to these questions. Okay, so the Q, you want to calculate your E cell, right? And then you know your E cell is going to equal to your E naught cell minus 1 over n times 0.25693 times your LMQ, right? So that is actually the equation that we got. Okay. So now you want to figure out the things that you can figure out, right? The data tells you you have two redox couple. Okay, and then it tells you the reduction potential of aluminum 3 plus. Negative 1.66. And then reduction potential of the Fe3 plus is 0.77 volt. Okay.
Can you get out these two equations yourself? Can you? Okay, so for the first one, I write aluminum 3 plus 3 electron, I give you aluminum, right? What do I write for the second one? Fe3 plus single electron, they give you Fe2 plus. How do I know I only add in one electron? It's not adding 3. Can the ion like Fe3 plus gain 3 electron and become Fe slowly? It's possible, right? But why do I just stop there? I write Fe3 plus and that's my reactant, Fe2 plus as my product. Okay, so to answer that, you have to really pay attention to the redox couple. Okay, so if you read this question carefully,
Do you see this? Do you see this too?
it's very important that you know what the redox couple you're actually talking about here, because a lot of things can change. Okay, so log redox couple specify your reactant and product. Okay, so when I say Fe3 plus gaining electrons, okay, I know my reactant very clear, right? Fe3 plus. So what's my product? The information of the product coming from this redox couple. Okay, since its base is Fe3 plus slash Fe2 plus, meaning that one place is your reactant and one place is your product. Okay, so that we cannot write Fe3 plus gaining 3 electrons become Fe, because that is not a specific redox reaction this question is actually discussing. Is that clear? Okay, so make sure you know how to write this equation properly. All right?
Okay. Get back to here. So up to this point, then you know these are the two reactions.
But you have a vortex cell, therefore you have to flip one of them before adding up. But you also end up with a positive inner cell, right? So who will be your lower? Aluminum, right? You need to actually flip your aluminum. Therefore, you know
your LoRa will be aluminum, becoming aluminum 3 plus 3 electron. So that your inner oxidation is going to equal to positive 1.66 volt. Okay. So apparently your G-rock will be Fe3 plus electron. They give you Fe2 plus. Then your reduction potential is 0.77 volt. Okay.
so after this, you want to actually know what's your overall equation for this redox reaction, right? And since to add up your LoRa and G-rock. But can you add up like this? You can't. Because the electron produced by your LoRa is not the same as the electron received by your G-rock, right? Therefore, what you need to do is actually you multiply
the 3 for your G-rock so that the electron
generated by your LoRa is again the same as the electron received by your G-rock.
Okay. How would that actually affect your reduction potential?
Since reduction potential is an intensive property, okay, it doesn't change no matter what coefficient you multiply for your reaction. Okay, so it's still the same. So
therefore, after you know you have balanced the electron transfer between the two half reactions, you can adding up. These two will cancel out. You end up with aluminum solid plus 3Fe 3 plus. They give you aluminum 3 plus 3 aluminum 2 sorry, iron 2 plus. Your E naught cell will equals to E naught us plus your E naught, which is 1.66 plus 0.77, which equals to 2.43 volts. Okay. How about the N? It should be clear to you. The electron got transferred between the two half reactions should equal to 3, right? So these are the information that you can get. Okay. But when you look at this, right now you have your E naught cell, you have your N. If you figure out your Q, then you can figure out your E cell, right? So how do you write your Q? The Q should be aluminum 3 plus first power Fe 2 plus to the Q. Denominator will be should I put aluminum here? Shouldn't, right? Because it's a pure solid. Therefore, this one should not be here. Okay? So once you know how to write out your chemical quotient, right? Let's start to plug in all the numbers. Your Al3 plus is 0.1, right? So it's 0.1 first power. Fe2 plus, it is 1 cube. Fe3 plus, 0.1 cube. Okay, so if you calculate this number, your Q is going to be equals to 100. Okay? So once you have all this information, you can calculate your E cell equals to E naught cell, which is 2.43 minus 1 over 3 electron times 0.025693 times LNQ. Q is 100. Okay, so you got 2.43 minus 0.039. So you know your E cell is going to equals to 2.39. That's how you solve this question. All right. Okay, so let's actually the question you're going to encounter for trying to get I the E cell, E naught cell, delta G naught, K and Q. Okay, very standard questions. Okay. All right, so the second things that we want to learn today is called the electroflapping. Okay, so this things is very, very similar to the next topic we want to talk about for the electrolysis. Okay. So in the galvanic cell, what we do is actually we put two half reactions together, where you can actually eventually create a E naught cell that is actually a positive number, right? That means actually this reaction will happen spontaneously and generate a bunch of electrons for you to use. Okay, so that's actually the galvanic cell or vortex cell. Okay, so the things we're going to do here is actually we're trying to reverse that process.
Okay, so if I put a bunch of electrons to my electrodes and forming a circuit, right? So you can actually force the chemical reaction that's not spontaneous to occur. Okay, so it's the flip side of the concept. Previous one is always generating electrons spontaneously. Now actually we want to actually apply the electrons to those type reaction to force it to happen. Okay, so
Instrument-wise, okay, it becomes much simpler because all you have is actually a big beaker. And you have two electrodes. Okay, you still have your anode. You still have your cathode. Okay, and these two will connect it to a big battery. Okay. Inside your containers, you are going to put a bunch of electrolytes or ionic species. Okay, so a lot of cations, a lot of anions. Okay, so when you put the batteries, okay, the electron will coming out on this side and then go to your cathode. Okay, so remember we say G-rock, right? So on your cathode, you still have the reduction reaction. Everything stays the same as how we described before. Okay, so electrons going to your cathode. So imagine that right now your electrode on your cathode is filling with a lot of electrons, right? And those electrons will attract the ions, okay, goes to your cathode, okay? And then after that, your ion inside your solution, okay, will your, okay, material is actually disappearing, right? So your ion will actually move to your anode to give up its electron, so you form a full circuit, okay? So idea is actually very simple, right? Cation go to your cathode, and go to your anode. Your anode still going to have your LoRa to occur. Okay, then you form this loop. Okay. So idea is actually if I drive, if I click enough volt from my battery, then actually drives not the chemical reactions. They won't happen spontaneously. Okay. So if today you put enough electrons, okay, then your care is going to be reduced. Okay, when they reduce, okay, what's really going to happen, like what you're going to see in the laboratory is that you start to see your electrons start to have some shiny things coating on it. Okay, so we call the process electroplating. Okay, so you start to coating things on the subjects that you want to coat them. Okay. So the one of the main things that CHEM1312 want you to know is that can you calculate how many kaons was deposited onto your electron? Okay, and this question is actually the thing to really memorize. Okay. So it looks actually quite complicated at first glance, but it is actually relatively simple. First term, grain of the product. Okay, how many grain of the things will be deposited onto your electrode? That's what it means. Okay, typically you are going to calculate this. Okay, so how do you know how many grain? Okay, since this is a reduction reactions, right? First, you have to calculate how many electrons you actually provide from your battery. Okay, so to calculate that, it's actually very simple. So we use these things on the numerator, A times S. A is actually telling you how many M I'm going to insert into my electron. Okay, S stands for how long.
Okay, so every time I just apply the electron into your electrode, we typically use M to describe the efficiency. Okay, and then you need to actually multiply your times to give you the overall charge. Okay, so A times S is very simple, just how many electrons I inject into that thing. So you can start to reduce the substance. Okay, so that's what's on the top. Okay, so let's actually the concept of overall how many electrons, right? But when we describe the product, we always use moles. Okay, therefore we actually convert electrons into how many moles of electrons. Okay, and that's actually conversion factors we use. Is your Faraday constant F. Okay, meaning that this will be how many more of electrons they're going to insert. Okay, and then the next thing is actually okay. Since I know, let's say I give you 2 more of electrons. Okay, then I need to know if I give you 1 more for chemical substance to actually form a product. For example, Fe2 plus, they become Fe. Okay, so 1 more of Fe2 plus, you will require 2 more of electron, so it becomes Fe solid. Right. So still NET over there. Again, it's actually how many more electrons they can reduce one species. Okay, so for example, I want to reduce one Fe2 plus into Fe, then I need 2 more of electrons. Okay, since you know the total mole of electrons from the things like that circle, divided by the required electrons to reduce 1 more of your product. Okay, that tells you, okay, that's how many more of product you're going to have. Okay, then multiply is molecular mass. Then you will know what the mass of the product will be. Okay, so that's why this equation has this specific form. Okay, so at the end of the day, that's the equation you're going to use. Okay, rate of the product will equal to m times time between the second. Okay, m times second divided by your Faraday constant divided by the mole of electron you need to reduce your product times its molar mass. Okay, so that is actually the overall equation. Okay, so that's the second thing that we want to become a master today. Okay, ideal-wise, very simple. Okay, all you need to do is actually just memorize this equation. Okay, G equals to A times S divided by NF times your molar mass. Okay. With that being said, then we can actually solve more questions now. Okay, it says, how many Columbus are required to reduce 10 grams of iron metals from a solution that contains aqueous iron 3 chloride? Okay, so Q is Columbus. Columbus means actually total number of electrons. Okay, which is your m times second. Okay, so that's actually what you're going to calculate. Okay, data. Okay, you have 10 grams of Fe, right? So Fe apparently is your product. Okay, so how do you get the Fe? It's from your iron 3 chloride, right? So you know is this. Right? That's actually how you get your Fe. So from here, you should see that the number of electrons that transfer is equals to 3, right? Because you start from Fe3 plus.
you end up with Fe. Okay. And then we also know that if you check out the molecular mass of your Fe, which is your product, you're going to get a value of 55.8 gram per mole. Okay, so those are the information that you can get. Okay. Then you use this equation I gave you, right? The grain of your product is going to equal to the n times second divided by your Faraday constant divided by the number of electrons that you need to produce one mole of your product. Multiply the molar mass of your product. Okay. So once you can write these things out, you should see that you have 10 grams of your product, right? So the first step is actually 10. You don't know the amp, you don't know the second. These are the things you need to calculate so you can get how many electrons that you inject into your electrode. Okay? N equal to 3. Faraday constant will be given, which is going to give you a number of 9.6485 times 10 to the fourth power. As the molar mass is 55.8. Okay, therefore your C is going to equals to 10 times 6 times 3 times 9.6485 times 10 to the fourth power divided by 55.8. And you're going to get a value of 5.19 times 10 to the fourth power Columbus. Okay. All right, so let's recap this one quickly. A few keywords. I guess I did not highlight keywords clear enough. Okay. Columbus, okay, is something that you will need to know, which is actually a product of m times second. Okay, and then it produced 10 grams of iron metals from a solution of iron 3 chloride. Okay. Iron 3 is important because that's how you get the information. And but because you know your final product is iron, but your reaction is actually iron 3. Therefore, you know you need 3 electrons to make that happen. That's how you get your N. Okay, so those are the keywords that you should know. Okay, and once you know you see this keyword Columbus, then you know the equation you can use is when equal to A times S over N times F, multiply your molar mass. Okay. All right, so let's do one more. Okay, here it says how many grams of manganese may be formed by passing 5 amp for 1.5 hours through the electrolytic cell that contains a molten NM4 salt. Okay, there's actually many keywords here that tells you what equation that you need to use. Okay, I highlight those things. Okay. So here it tells you the M, it tells you the time, right? So every time you see M, see the time, then you know the equation you use is actually grain of your product equals to M times second divided by NF times your molecular mass. Okay. So the question is really asks you the grain of your product, right? And then the product here will be manganese. Okay, so your Mn. Okay, data that you have, you know your A equals to 5. Your S equals to 1.5 hours. Okay, here is actually time, the things you need to be careful. When you talk about time, it has like a unit of second. Okay, so you need to do this. 1.5 times 60 minutes times 60 seconds. Therefore, you have that many seconds. Okay, what's your N? That is coming from an M4, so right? And then going to 4 equivalent electrons. So this will equal to 4. Okay. What's your molar mass? The molar mass of who? Manganese, right? So Mn, if you check out periodic table, you're going to get 54.9. Okay. So you know your brain is going to equal to A times S. NET times your periodic constant times your molar mass, right? So it will be 5 times 5400 divided by 4 times 9.6485 times 10 to the 4th power times 54.9. And this will give you a value of 3.84 gram. Okay, so this is actually how you do this question number 4. All right. Any question for this? A is the N. F is the periodic constant. Okay, which you're going to find that in the, so every time we do the exam, you always get a sheet with the periodic table and a bunch of constant below, right? Yeah, it will be there. Yeah, use that constant. Question 1. Here, this. And everyone who has calculated do this calculation. Is this the right number? 2.1 times, is that why you got 2 times 10 to the negative 1? 2.17. You could probably right. Okay. And then if you also do my calculation wrong, I will double check and then get back to you next time. Okay. Yeah, so if you take the exponential on both sides, then you should get like 2.17. Yeah. So sometimes, but let's take the logic. Okay, so the key is actually can actually follow the popular bubble problem. Okay. All right, so Okay, we only have a few minutes left. Let's talk about some of the simple concepts for the remaining part of this. Okay.
So the very last part we want to talk about is called the electrolysis. Okay, it's basically the same as your electroplating. But the question you're going to be asked is not like how many grain of product forming on your electron. It's not like that. Okay. The question you're going to encounter is that you will ask you if I have a proper setup. Okay. If I grow different species, can you predict which species is going to form on your capsule or your anode? Okay, so those are the things that you will be asked for the electrolysis type question. Okay, so let's start from the very simple one. If today you only have a Newton salt inside your beaker, okay, then you insert your electron, you provide the electricity using your battery. Okay, so electron go through your capsule, can move to your cathode and reduce. Okay, and go to your anode and oxidize. Okay, so the principle over there is really simple. It's actually nothing you need to actually worry about. Okay, it's just a single species. Okay, if just one type of Newton salt, then your anion go to your cathode and anion go to your anode. Okay, it's as simple as that. Okay, for example, if today I throw in things, let's say the Newton lithium chloride. Okay, if I put a lithium chloride inside my solution, okay, only lithium chloride, nothing else, no water, nothing else, only lithium chloride, Newton. Okay, so you have lithium plus CO minus inside your solution. And you put in the electrodes, you put in a good potential to actually drive the reaction to happen. Okay, so what I want to see on the anode. Okay, so let's do this. Okay, remember, cation go to your cathode, anion go to your anode. Okay, so let's start from the anode first. Okay, so for your lithium chloride, that's the example we did, right? So what's your anion? Cl minus, right? It's going to move to your anode, right? And it's going to react and oxidize, right? So Cl minus got oxidized is going to become CO2. Okay, plus you give out 2 electrons, so you can form this circuit, right? So you know, if there is a simple case, your Cl will go to your anode, give you CO2. How about things on the cathode? So you have to look for your cations, right? Your lithium is going to gain the electron from your cathode. So Li plus, any electron, they give you Li solid. So lithium goes to cathode and give you the Li solid. Okay, so let's calculate this. If you only have one single Newton salt. Okay? So now things will get a little more complicated. If today I throw in 2 different Newton salts. Okay? For example, we start from lithium chloride, right? So now we have, let's say, magnesium bromide. Okay? So this actually, we actually move to a second one. Okay, mixture of the Newton salt. Okay, so still, your cation will still move to your cathode. Anion will still move to your anode. Everything's still the same, right? But who get to there first? It's actually a question you guys are going to encounter. Okay, so the rules that we want you to memorize. Okay. When the things move to your cathode, it's the reduction reactions, right? Therefore, for every single cation, you're going to have this corresponding reduction potential. Okay, whoever has a less negative reduction potential will be the first one got reduced. Okay, so the negative side that we see for this reduction potential meaning how many volts is required to make the reaction to happen. Okay, if you essentially have less negative, then it will happen first. Okay, the same concept applies to your anode. Okay, but you can just use your reduction potential. You want to use your oxidation potential. Okay, whoever has less negative oxidation potential, then you will got oxide first. Okay, so this is actually the concept. So everybody follow the concept? We're just talking about concept today. We're not going to give you an example today. We're going to go through the example on Thursday. Okay, but does everybody follow me? Because that's like one more layer we have to add in before we finish this. But so far so good. Okay. The most complicated case we're going to encounter for chapter 14 and 17 here is that you have an aqueous melted salt. Okay, so the reason this is more complicated is that because we can electrolysis our water as well. Okay, so water is actually a very interesting molecule. It can be oxidized and reduced. Okay, if you add water oxide, you produce O2, and reduce, you produce H2. Okay, therefore you should actually memorize the reduction potential and the oxidation potential of your water. Okay, so if you have an aqueous salt solution, okay, then for your capsule, you can actually compare the reduction potential of your gas and the reduction potential of water. Okay, so if water has a less negative reduction potential, then you actually reduce your water instead of reduce the gas. Okay, similarly, for the anions, okay, you can look at whoever have a less negative oxidation potential, it will be oxide first. Okay, so you have to consider the role of H2O in those aqueous salt solution. Okay, but concept-wise, it's always the same. Whoever have a less negative reduction potential or less negative oxidation potential, there will be the species that reduce or oxidize first. Okay, so we'll go through those examples on Thursday. Okay, but concept-wise, it's really simple. And that will actually conclude chapter 17. Okay, so that's it for today. Thank you.